For this video, we will be discussing acceleration. So in your notes packet, this is section 11.3. So to begin with, we're going to start talking about acceleration and our definition for acceleration. So acceleration is a vector. Remember, all vectors need a direction and some sort of magnitude. And if you remember, magnitude is just the number associated with this. So just like velocity and displacement, all three of these are vectors. What acceleration is it is the rate at which velocity changes, or you could say it's how quickly the velocity changes. Velocity can be changed in three different ways. That means you can change your acceleration in three different ways. You can change it either by speeding up, slowing down, or just by changing your direction. Since acceleration is a vector, by changing the direction, technically you're changing your acceleration as well. When we look at instantaneous acceleration is the rate at which a velocity changes in a given moment. So right now, which is opposed to average acceleration, which would be how quickly you're changing over the entire trip or over a certain interval of time. This is just at a single moment in time. When we go to look at acceleration and how to calculate it, so we have A equals V sub F minus V sub I all over T. When we look at what each one of these represents, A is your acceleration, and acceleration is measured in the units meters per second squared. VF stands for your final velocity, and remember this is a little f down below. And this is measured in meters per second. VI is your initial velocity or your starting velocity, and this is also measured in meters per second. And then of course T is time, and that is measured in seconds. So if we look at this next problem, your first problem down below, if a car stops at a stop sign and you increase your speed to 48 kilometers an hour in 60 hours, I had to change the seconds unit here into hours so that the two time units match. I want to know what your acceleration is. So the first thing we're going to do is we're going to go through and identify all of the variables. So the stop sign, or being stopped, is one. 48 kilometers an hour is another, and then 60 hours is a third one. And then so your initial velocity is being stopped, so that's going to be 0. Your final velocity, because that's what you're increasing your speed to, is 48 kilometers an hour. And then our time obviously is 60 hours. And then we're looking for our acceleration. So when we look at our formula, we need to rewrite this every single time. So A equals VF minus VI over T. And then we need to plug in our numbers for this. So we know VF is 48. We know VI is 0, so that'll go in there. And then we know our time is 60. So we have 48 minus 0 divided by 60. And we know if you take if you take anything minus 0, it should just be what that is. So we have 48 divided by 60. And if you punch this into your calculator, it will give you your number. And so what we end up getting is 0.8 kilometers per hour squared. The big thing with these units is it's always going to be a unit of distance, so that's our kilometers, over whatever our unit for time is, but it's going to be squared. So that's the big thing to make sure of. So just like with before, we had said back on this previous slide, I go back, it's meters per second squared. So now we're dealing with hours squared. And that's just what our unit is. We don't have to actually square our time. That's just the unit. If we look at this next problem, so a cat is chasing a mouse at 16 kilometers an hour. When the mouse runs into its den, the cat slides to a stop in 5 seconds. So what is the cat's acceleration? I have already highlighted all of the variables for this. So our 16 kilometers an hour, we're going to change into meters per second so that our seconds here match our seconds over here. So that is going to be our initial velocity. I know it's kind of hard to see, but that is our VI because that's what the cat's speed is starting at, or its velocity is starting at. Then it's going to slide to a stop. So that's our VF, which equals 0. And then we have our time. And our acceleration is what is unknown. So if we write out our formula, we have A equals VF minus VI all over T. So if we plug in our numbers, our final velocity now, since we're coming to a stop, is 0. So that's why that's 0. Then we have minus our initial velocity, which is 16. And then we plug in our time, which is 5. And yes, that's a 5. It's not an S. So if you work this out, again, 0 minus 16 should be negative 16. And then we're going to take that divided by 5. And when we punch this into our calculators, you should get negative 3.2 meters per second squared. And so that's how you would go through and do acceleration problems. The biggest thing is trying to figure out what your initial and final velocities are. Okay, for the graphing acceleration, so we're looking at this type of graph here. If you notice, we've got speed on the side, we've got time over here, opposed to our other graph we looked at the other day in class. What we had on our Y was our distance, and then down here was time. So first thing we're going to look at is what is an appropriate title for the graph. So anytime you are graphing something, what the title should be is always whatever is on the Y versus whatever is on the X. So in this instance, our speed is on the Y, our time is on the X. So it should be a speed versus time graph. So then when we're looking at what does the slope of the graph tell us, so again, slope is rise over run. So in this instance, our rise is our speed, our run is our time, so speed over time. And so when you look back at our equations, speed over time, or a change in speed over time, is just acceleration. So the slope of all of these lines should tell us what our acceleration is if we go through and calculate them. First thing we are going to do is when looking at a speed time graph, how can you tell if an object is accelerating? So just looking at this, it might be difficult to tell when an object is accelerating. So what we're going to be looking for is if there's a positive slope on a line. And what a positive slope is going to look like is if this is our y-axis and our x-axis, it should be pointing up in some way, shape, or form. So any point where there's a positive slope, you're going to be accelerating. So just looking at this graph, I can see 1, 2, 3 different points. I'm only going to point out 2. So one point is from time 0 to 15. So it's this line here that I've highlighted. So during this entire time interval, so for that 15 minutes here, it's going to be accelerating. It's going to have a positive acceleration. For a second point, I want to sorry about that. For a second point, I want you guys to identify a second positive slope from, and make sure you tell me it's between this time and this time. For the next one, we are going to look to see if it's decelerating or slowing down